Hello everyone. Here we look at topics 4 and 5 of Exam 1, Exponential Functions and Differentiation. First, some theory of exponential functions. We formally define the inverse of the natural logarithmic function f of x equaling the natural log of x as the natural exponential function. So I chose at this point to call it g of x equaling e to the x. And we want to talk about the theory of inverse functions to have a full understanding. And the formal definition for an inverse function, as you should recall from previous courses, is that a function g is the inverse of a function f if the composition f composed with, so remember this little circle symbol, this little bubble symbol, means composition, or you read it as composed with. So f composed with g of x is equal to x, and that has the restriction that for all x such that the range of g is the domain of f. And then similarly, the reverse of that has to be true. The composition of g with f, or g composed with f of x, must also equal x, and we have a restriction there. A lot of times in mathematics we'll use a mapping to picture some abstract concepts. So here what we're going to do is we're going to draw an oval, and let's say that this represents the domain of the function f. And we have all these elements in the domain of f, everything that satisfies the domain. For example, if f of x is the square root of x, then the domain of f is that x must be greater than or equal to 0. So here we're talking about it in the abstract sense. So if we focus on just, let's say, one element x, and we take that element and we send it through the function f, and we can indicate that with an arrow and even put the name of the function on top of the arrow, we create the image f of x. And then if we take all the elements in the domain of f and send them through the function f, we then create a new set which we'll call the range of f. Now, in order to define the inverse, if the range of f is in the domain of g, then the inverse function should undo whatever f did. So if we take the result f of x, if g is in fact the inverse function, we send f of x through g, and if it's the inverse, it's going to bring us back to x. And that is g of f of x. That is the composition of g with f. So you can see why these statements have to be true. You could do it in reverse as well. That is, if you start with an x over here in the domain of g, send it through g, you get the element g of x, but then you send that through, so that would be the range of g, must be the domain of f, and then you could send g through f, and that would be f of g of x, and that also has to be x. So you can see why those two definitions have to be true with that little mapping scheme. Excuse me. Graphically, inverse functions are actually reflections in the line y equaling x. So just to show you what I mean by that, if we have a function, and for now just trust me that this function has an inverse, so let me just draw the Cartesian system, and let me say this is actually the square root of x minus 1, but we won't even worry about naming the function. Let's just call it f. And trust me that it has an inverse, and if it does have an inverse, then the inverse is a reflection in the line y equaling x. And the line y equaling x is a line that bisects the first and third quadrants. And you might even recall that when finding inverse functions, you had to reverse the x and y values at some point, interchange them. So x became y and y became x. That's basically what happens here. The point 1, 0 in the reflection becomes the point 0, 1, and then you could use your spatial senses kind of folding this over on the dotted line, and you would see that the inverse g would look something like that. So those are a couple important things to remember about inverse functions. And with that, we can easily graph the natural log of x. I purposely waited on graphing the natural log of x until we talked about e to the x and those two concepts, because now we know what e to the x looks like. I mean, you can even plot a table of values as is suggested here. Like here's x and g of x equaling e to the x. So let's say if x is 0, I'm going in the middle of the table, e to the 0 would be 1. If x is 1, e to the first is about 2.71828. If x is 2, e squared is about 7 point something. Let me check it out on my calculator. Let's see, e raised to the second is 7.389, so let me just say about 7.4. Go in the opposite direction, negative 1. E to the negative 1 is about 0.37. If x is negative 2, just for the sake of doing it, e to the negative 2 is 0.135. It's going to get smaller and smaller. Never gets negative though. Okay, and then if you want to plot those, just make a rough sketch here. Okay, all you need to really know about the exponential function, it passes through the point 0, 1, and e to the x is just exponential growth, so it's going to look like that. I mean, if you want to plot more points, like when x is 1, it's 2.7, so that's 2 and that's 3, it's roughly here. But just continue, you can plot the other points as well. When x is negative 1, it's about 0.37, so right about there. And then it gets closer and closer to the x-axis. So it rides the x-axis here, and then it's just simply exponential growth. So that's g of x equaling e to the x. And everybody should know what e to the x looks like. So you really shouldn't even have to create the table of ordered pairs. But the point here is to now use the concept of the inverse functions to graph the natural log of x. So again, since we've defined them to be inverses, graphically, the reflections in the line y equaling x, there's the line y equaling x, bisecting the first and third quadrants. The point 0, 1 here now becomes the point 1, 0 in the reflection, and then using your spatial senses, see the negative x-axis, which was a horizontal asymptote, will now become the negative y-axis, which is a vertical asymptote, and you could use your spatial senses to see that that roughly is the graph of f of x equaling the natural log of x. Okay, so it's very easy to graph the natural log of x, and you can see how we've defined it before. X must be greater than 0, and how less than, when x is between 0 and 1, it's negative. When x is equal to 1, natural log of 1 is 0. And when x is greater than 1, natural log of x is positive. So that's a little bit of theory. Going further, we have what we call inverse properties. And they're stated here. Natural log of e to the x is equal to x, and e to the natural log of x is x. There's no cancellations happening. It's a consequence of inverses. I just want to prove both of these to you quickly. So here's the reasons why. We've defined natural log of x and e to the x to be inverses. By definition of inverses, one was that f composed with g of x had to be equal to x. And so here let's calculate what the left-hand side is. We know the right-hand side has to equal x. Well, this composition is just shorthand. This little bubble symbol is shorthand for f of g of x. So g of x is the inner function, and f is the outer function. If I then replace g of x by e to the x, we have f of e to the x must be equal to x. And then this just simply means, don't make this harder than it is, because this is f of this, e to the x. Like, for example, if f of x is the natural log of x, then f of 2 would be the natural log of 2. We're just replacing the x in f of x by the number 2. So now we're replacing the x in f of x by the expression by the function e to the x. So f of x is the natural log of x, so this becomes the natural log of e to the x, and that has to equal x, and that's our first inverse property. And the second inverse property can be proven or shown by calculating g composed of f of x, because that must equal x. And so again, that's just shorthand, putting in a working form, g of f of x the inner function, g the outer function. Let's literally replace f of x by what it was defined to be, the natural log of x. So g of the natural log of x is x. And again, this is just like we talked about moments ago. G of the natural log of x means wherever I see an x here in g of x, I'm going to replace that x by the natural log of x. So this becomes e, because that's what g is, e to the x. So that would be e raised to the natural log of x. It has to be x. And that's the second inverse property. Okay, so here's a couple examples of simplifying. Whenever you see e and ln hanging around together, you know something's going on with these inverse properties. Here it says to simplify. Now the first question, it's understood that the argument that belongs to the natural log is x to the 5th e cubed. You could put parentheses around that if you like. And to simplify, we could use our algebraic log properties, the first of which is the log of a product. And so we'd have the natural log of x to the 5th plus the natural log of e cubed. But then we can go further with the inverse properties. In particular, natural log of x to the 5th, the power property says we can bring the 5 out in front of the natural log of x. And now note, by our inverse property, the natural log of e to the 3rd is just simply 3. Okay, so that's one example. Here in this example, in order to exercise the property, it's e to the natural log of x. The coefficient of that logarithm, that's the power on the base of e, has to be 1 in order to apply the property and get the argument out of that. So here we actually have to condense this exponent. So the first thing is to bring up the coefficients to be the powers on the arguments of those individual logarithms. So we'll have e to the natural log of x cubed plus the natural log of y to the 4th. Then we could recognize that this is a sum of logs, which we know came from a product. So e to the natural log of x cubed y to the fourth. And now by the inverse property, e to the natural log of something is just that something. So x cubed y to the fourth. Okay, and now we get to the theorem for the derivatives of e. So we're going to state the chain rule version. I left these empty so we could write them down together. You need to get used to writing down the formulas. So I have the standard disclaimer. First of all, just the derivative with respect to x of e to the x. Okay, easiest formula you can imagine. Derivative of e to the x is e to the x. But then we have the chain rule version. Derivative with respect to x of e to the u. Okay, just remember, make sure you are comfortable with this notation. Understand that it means the derivative with respect to x of this type of thing is equal to this result. It's shorthand notation, as we've talked about, to indicate our formulas. And it's the chain rule version, so the derivative of e to the u, well, if the derivative of e to the x was e to the x, derivative of e to the u is e to the u, but as a consequence of the chain rule, times the derivative of that power on the base of e, denoted du dx. So there's our two new formulas that you have to memorize, and they are considered common knowledge. And before we see some examples, we'll take the time to prove the formula. I wrote it out using this verbiage because of the nature of the way that we actually show the proof. So instead of using the shorthand notation to indicate the derivative, I literally wrote if y equals e to the u, then dy dx is e to the u du dx. Now this will be a required proof, and I'll summarize before we get tested on our first proof quiz. I'll summarize that for you during our live lectures. But what you want to do here is start with what's given. So let's just say let y equal e to the u. What we're going to do here is actually use logarithmic differentiation. And we're going to take the natural log of both sides of the equation. So the natural log of y is the natural log of e to the u. So let me put in a different color in red here off to the side. When I do something, I'll mention what type of thing we did. This was logarithmic differentiation. Log of both sides. But then notice that, well, the natural log of y we can't do anything with, but the natural log of e to the u, by our inverse property, is just simply u. The inverse property. Because the natural log of e to the x is x, so the natural log of e to the u is u. Okay, now we can start the differentiation, because we've actually proven previously what the derivative of the natural log of y is. Now I'm throwing this ddx notation in front of each side because it is implicit differentiation. You don't have to use it. You can jump right to the differentiation, which is when I differentiate the natural log of y, we get a fraction. Log goes away, y goes in the denominator, its derivative dy dx in the numerator. And then on the right hand side, if you introduce the ddx notation, all you have to do is be able to read it. It's saying the derivative of u with respect to x, or simply enough, du dx. Okay, and then we're going to multiply both sides. So this is differentiating. And then we're going to multiply both sides of the equation to solve for dy dx by y. So dy dx is y times du dx. You can show that if you like. It's not necessary, but if you want to show you're multiplying both sides by y, that's fine. And then finally, you just back substitute. Y originally was e to the u. So dy dx is e to the u, du dx, and that ends the proof. Okay, so this step was just multiply by y, and this step was back substitute. Okay, if you like a little bit of guidance there. You don't need to write to me what's in red, that's just to help you in the notes. But what I've shown here on the left in blue are things I need to see when you prove this for me. Okay, so we will come back. I'm going to stop right there. We'll call that part 1, and we'll come back for part 2, which will be just simply a bunch of derivative problems.